A differential equation of this type is called a first-order differential equation. The differential equation we have seen so far have been special cases of this, where this was a constant and this was 0. So now we will see how we can solve this generally. Here f and g are known functions and y is the unknown function we are seeking. We will show with a concrete example how you solve an equation of this form. Here is the first order differential equation we want to solve. So here we have suppressed the x. So y means the function of x. And f of x we have chosen to be 2x and g of x chosen to be x. The technique for solving this one is similar to what we did before. 2x is an inner derivative of this one. So let's multiply both sides by this. These two linear equations are equivalent, because if this is true, then this must be true, and vice versa. If this is true, it follows that that must be true. So they have the same solutions. And if we multiply in the exponential, we get this one. And now we see that we can rewrite the left-hand side as a derivative of a product. And the product in this case is this. So the left-hand side we can write like this. Because if I take the derivative of this, first take the derivative of that one, it gives me this, times this, which is this one. And then I have to take y times the derivative of this one. Then I have to take the outer derivative, giving me this, and the inner derivative, giving me this. The derivative of this function should be equal to this, and that means that the function inside the parenthesis is an antiderivative to this one. So we see that if we take the derivative of this one, we get the outer derivative here, and the inner derivative 2x almost gives us this, but then we have to multiply by a half. And then we have to add the integration constant. Now we can just divide both sides by this one, or what is the same thing, multiply both sides by this raised to the power of minus this. Here we just get 1. And if we multiply in, again this is equal to 1. So finally we get this. And thereby we have found the solution to this equation here. Here c can be any arbitrary constant. The example we just saw can be easily generalized to arbitrary functions f and g. And the solution is given by this one. And here capital F is one antiderivative to f. The proof is shown in the book, but we will not prove it here. Instead we will see the example now of how we can use this to solve an equation. So let's say we want to solve this one. And in this case here we have f of x. And this is g of x. Then using the general solution we just saw. Then first we have to find an antiderivative of x squared. And that's just x to the third divided by 3. And here we don't have to add a c, since we are only asking for one antiderivative, and then this will hold. Then we should take the antiderivative of 4x squared times the antiderivative again. Here we can use the antiderivative by substitution. And let's call this z. then we get the derivative x squared. So this set is equal to x squared times dx. And substituting that in here, then x squared dx is just this set. And we have 4 remaining, and e raised to the power z. And finding an antiderivative of this one is easy. Since it's just the same, plus a constant. And here it's important that we keep the parentheses, because c will also be multiplied by this. Substituting back in here, and then multiplying in. Will give this after simplifying. So this times this will multiply to 1. So you're only left with 4. And then we have found a solution to this equation using this general formula here.